And that's going to lead us into general senses. We're going to look at general senses first, sense of touch, okay? And then we'll dive into all the special senses. See how far we get today.
I'm not understanding how the mucous membranes are somatic. I mean, like, how can we control our mucous membranes?
You can control what you put in there, yep.
Oh, just...
You control what goes in your nose, mouth, butt, all that stuff.
Okay, just control what goes in, but not make them do something
No,
by our will, per se.
no, but my will is to say I'm not going to put that food in my mouth because I don't like it.
Okay.
Okay. And it's covering up, to be honest, muscles within there as well, right? We got muscles all throughout that region as well. Well, you probably don't know because we haven't gone over it yet. So you probably don't. That's perfectly fine. But we have a plethora of various different muscles within the oral cavity, in the back of the throat, that the mucous membranes will cover. And so, yeah, so most of those are skeletal in nature. We can control. So anything that covers the skeletal muscle is going to be something that's under the somatic realm. Okay.
Thank you.
You're welcome. All right. So let's look at touch. We have a huge amount of tactile receptors, and tactile is touch, and touch is mechanical, right? This is mechanical, right? I am touching my hand, and that is mechanical, okay? Whether it's light, whether it's really tough and hard, okay? Whether it's really deep or whether it's really light, all that stuff, okay? Tactile is mechanical, okay? Touch. This is touch, okay? And to touch is mechanical. And we have all of these types within our skin, within our mucous membranes. And as you can see, we can have some that are very boring. And by boring, I mean they're just basically a free nerve ending. And those are unencapsulated, right? They don't have a special connective tissue wrapping around them. So they're very basic in structure. And we have some that have a capsule around it, okay? Where it'll have some kind of connective tissue wrapping. This is my free nerve ending. And some of them have a capsule around it here. And that will give it a lot more sensitivity, okay? And they have a lot more of a complex structure. It's just basically neurolemmacytes, all right, that kind of wrap around this thing. So same thing that it did within the periphery, wrapping around axons. We're going to find that around some specialized nerve endings here. So we have some that are encapsulated and some that are not encapsulated. Maybe trying to differentiate between an encapsulated mechanoreceptor and an unencapsulated mechanoreceptor. That always makes a good question. Not necessarily short answer, all right, but that would make a pretty good question in any vein. So here are my 3 unencapsulated tactile receptors, unencapsulated mechanoreceptors. Free nerve endings, root hair plexus, and this thing called a tactile disc. Old school name is Merkel cells. I would know both of those, to be honest. Tactile disc or tactile cells, or Merkel cells. It honestly depends on the book. Anatomist books, I feel like I got to sneeze, but anatomy books will tend to use the word tactile. Oh my gosh, excuse me. I am so sorry. I couldn't get to the button fast enough. Tactile disc is used by anatomist books. Merkel cells will be used by physiologists more. Why not switch? I don't know. They're trying to, but physiologists are pretty slow to change terminologies for whatever reason. So we have free nerve endings, root hair plexus, and this thing that I'm going to try to use, tactile disc or Merkel cells. Where they're at is usually a good question, and what they pick up is usually a question I ask, or is it tonic or phasic? I ask one or two usually of all of those, okay? So, okay. And that's pretty much what I have. And you're like, gosh darn it, he's asking everything. Well, I'm not going to ask everything. I'm going to ask one or two of them, okay? Which I guess isn't everything. Free nerve endings. These are what you would think. Here's a free nerve ending. That is uninspiring, pretty basic, pretty simple. Okay. These can be phasic, these can be tonic. All right. As you can kind of see, they're in the skin. You could say mucous membranes, but mucous membranes is just what? Epithelial and connective tissue. So skin, basically, wet skin, if you want to simplify it in your head. Free nerve endings, because they're kind of scattered all about, they pick up pretty much anything and everything. But all of this mechanical, okay? This is not mechanical, right? That's more temperature related. But this is an exposed, ready to fire nerve. So they are literally going to respond to pretty much anything and everything. Okay. Have you ever whacked your finger or thumb with a hammer? I'm going to assume most of you have. Okay. When you do that, it's painful as hell. It gets really hot in there, and there's an increase in pressure. And all of that's brought in by basically these free nerve endings, along with a bunch of other people. But free nerve endings bring in all of that information. Okay. So whether you've cut yourself, whether you've burned yourself, or whether you have a little bit of pressure on the outside of your skin there, free nerve endings are usually the ones involved in helping to bring that in. Okay. Root hair plexus is only in one location. Root hair plexus is only found wrapped around a hair follicle. Okay. Only wrapped around a hair follicle. It's the only place you see it. Okay. It's the only place you see it. It is phasic. There is no information coming in from my arm from a root hair plexus unless something falls on it. Okay, if I grab this Post-it note and lay it over the top of my little hairs there, now they're firing. It makes me itch. Okay, but as soon as something lands on that hair, it bends the hair. Who picks it up? The root hair plexus picks it up. So it's only bringing information in unless stimulus changes. Nothing on it, not firing. As soon as something starts crawling on me, crawling on my hairs, I'm going to feel it. Okay. Lastly is tactile. And tactile disc only responds to light touch, but it's always on. Okay. It's always on. So as soon as somebody comes up and starts touching it, boom, it immediately sends it. All right. We're going to see some other light touch as well, but tactile disc or Merkel cells, okay, are there within the bottommost layer of that epidermis. Okay. So that's really superficial. So these are always going to be on, bringing us information if anything should lightly touch us. Okay. We got light touch. I've got hair movement. I've got everything. okay, with a tactile disc, root hair plexus, free nerve ending, respectively. And there's the Merkel cell, okay, and there's the tactile disc and the little tactile cell that extends off of the disc, okay. Again, very basic, very basic. Compared to my encapsulated ones, these are very complex here. Okay. You're also seeing here something that we're not going to get into. Some of these have myelin around them. Some of them do not. Okay. This has to go with that concept of slow or fast pain. Some pain is brought in at around 25-ish miles per hour. That's pretty damn fast. Some pain comes in very slowly, okay, maybe a couple miles per hour. And that has to deal with whether or not some of these are myelinated or unmyelinated, okay? So if you were to see a picture, I mean, you could deduce that, right? If something's myelinated, it speeds up a nerve impulse. You don't need to know the specific speed or anything like that. But if something's myelinated, it speeds it up, okay? So let's think about that for a quick second. If we have pain that can come in fast or slow, what would be an advantage to that? Well, slow pain allows me to adapt to it. Okay. And as long as it wasn't, causing some kind of severe damage to a joint, which would honestly be a lot more various different types of fast ones, but it allows me to be able to handle the pain, deal with the pain, and continue doing whatever it is that I'm doing. Allows me to maybe get out of harm's way. That allows me to actually, finish the job. And by job, I'm not saying, I'm working at assembly line or something like that. I'm working to get food. Remember, this is all hardwired to be kind of who we evolved from, right? Hunter-gatherers type of thing, right? So even though I might get stuck with something, a thorn, as long as it's not causing me some severe pain, I can continue to hunt whatever it is I'm looking for, okay, until I can get around and pull that thorn out of my butt, all right? So the slow receptors or fast receptors, I mean, that's great. Fast receptors brings it in quick, allows me to get the hell away from that pain. Slow pain allows me to, adapt a little bit to it, be able to finish the thing, okay? You've been in pain before, all right? Some like debilitating. Just think if it was debilitating all the time. That would suck. So those those encapsulated tactile receptors, as you can see, they have a lot more going on here, a lot more jazz associated with them. These are, again, I hate new terms, but I'm going to try my damnedest to use end bulb, bulbous corpuscles, which Ruffini, oh my gosh, so much easier to remember. Lamellated corpuscles and tactile corpuscles. And their old school names, man, they tell you exactly what in the heck they're doing. That's what sucks about it. I'm going to go Pacinian and Meissner's first. For Pacinian, I always thought of the Pacific Ocean. PAC of Pacinian, PAC of Pacific. The Pacific Ocean is deep. It allows me to detect deep pressure, and coarse touch is deep touch. Okay. So yeah, the Pacific Ocean is deep. And the Pacinian corpuscles, they are deeper. Dermis is deep to the epidermis. Hypodermis is deep to all that. Organs are deep to all that. Everything is deep. Nothing's very superficial here at all. Okay. So these are deep receptors in the skin. They detect deep pressure and deep touch. Pacific Ocean is deep. A Meissner, okay? A Meissner is somebody who's old and crotchety, and it takes very little to set him off, okay? Meissner's corpuscles respond to light touch, Okay, you can see they do a lot of other things as well. I mean, it's that discriminative touch. Close your eyes. I can put a paper clip into your fingertips there, and I can say, feel that. What is it? And you touch it, and you would, ta-da, be able to tell me. Okay, it's going to that, that association area right next to the proprioceptive region of the brain. So yes, okay, there's multiple things going on there, but these are the receptors that pick it up. Meisner's. They changed it to tactile corpuscles instead of Meissner's corpuscles. So I'm going to try. I will put tactile. Okay, I will put tactile on the exam if I have to ask it, which I probably will. And I'll put lamellated corpuscles. Okay, and if we look at them, lamellated is a lot more complex. Okay, there than Meissner's. Oops, wrong way. These are in the dermal papillae, okay, and that's up close to the epidermis. So, as you can see, these are both phasic. So they're only active when they're being touched, okay? Meissner, light touched, only responds when someone's touching, okay? Tactile disc is always on, okay, and brings us light touch. You find these specifically in that basal layer. You can see that these are right underneath the damn thing in that dermal papillae, this region right here, right within the dermis. So you can see both of these are pretty similar. Okay, they both bring about light touch, similar. But what's different? One's encapsulated and one's not encapsulated. One's in the epidermis, one's semantics, just right underneath the dermis, or just right underneath the epidermis. Okay, one's tonic, one's phasic. So you can see how this one can be commonly confused, and it usually is in the exam. I have some encapsulated receptors that are always on, and those are bulbous and the end bulb. The end bulb is kind of vibration is its kind of claim to fame. Direct pressure, or I'm sorry, detect pressure, but vibration is the one that I would remember. That's usually what it is. You could see this is located in the dermis or mucous membrane. So, but this is always on. It's bringing about vibrations. And as you sit there and talk, I mean, I can feel my mucous membranes vibrating as I'm producing sound, as it's coming up out of my mouth. That's the end bulb bringing us that information. Okay. It also is going to allow me to feel if something's moving around, and those are vibrations that I'm feeling. So that allows me to know I need to keep chewing so I can kill that thing before it does something bad to me inside my mouth. Again, all of these are here to allow us to survive, interact with the environment, right? Bulbous or Ruffini. This one is kind of weird looking. This one right here is Ruffini. This is Ruffini right here. Roof. Okay. It detects kind of a continuous type of pressure, deep or skin distortion. So it's working with the dermis, it's working with the subcutaneous layer. It, kind of continuous deep pressure. It's tonic. It's always on. So it has to be continuous. Okay. It has to be continuous if it's always on. This is a very simplistic representation of pain. Again, it can be somatic. It can be visceral. They'll go up kind of same pathways as is kind of said there in bullet number 2. And And they can go up and be interpreted into really a number of different somatosensory areas, because it'll spread the pain out. It spreads the pain out, guys, because of what happens during their development in utero. And we don't have time to do embryology, but a lot of these organs and the accompanying muscles that surround them and the skin that surrounds that little region, they all develop in what are called somites, various different levels of the cells that differentiate when you go from, zygote to blastocyst, as it's dividing and dividing and dividing, and gives us my 3 germ layers. And so when it comes to this concept of referred pain, I mean, when you look at this pain map, it doesn't make any damn sense. Okay. You can see kind of heart goes into down that left kind of pec area, down into left arm. Well, it develops in the same region as the nerves that supply that area, T1 through T5. Well, for men it does. For women, it can go down both arms because they're unique. But you can see kind of liver and gallbladder. Gallbladder pain is associated with that subscapular region on the right side. They don't have, do they have? Yeah, the appendix can be over the umbilicus. It's usually a little bit lower, called McBurney's point. But again, this referred pain has to go with where these things developed in utero. And unfortunately, we don't have time. So it's kind of hard to narrow down a lot of referred pain, because you could see the referred pain could be down my left arm. My left arm's tingling. Well, let's look at my arm. Nothing's going on. But if you have left arm tingly pain, that's always associated with signs of having a heart attack or, angina. So these referred pain patterns they're fantastic. If you can figure out and know some of these, they're actually really good from a diagnostic standpoint. But they are very difficult to pinpoint and sometimes figure out where in the hell it's coming from, just because of the multitudes of change that occurs when it goes from a collection of cells that are dividing into a very complex adult looking structure there. So so that's what's kind of going on there. Plus, I mean, how do you stop pain? That's even more complex. Have you ever, it always comes down to whacking my thumb with a hammer. Have you ever hit your thumb with a hammer? Anybody?
Yes.
What did you do after you whacked your little thumb with that hammer? Besides cuss, because that's a given.
I probably shook my hand or something.
You shook your hand. What the heck? Why? Why would you shake your hand? Because the same damn thing that carries pain can also carry the sense of touch. I mean, my thumb is moving through the air. Okay. It's going back and forth, back and forth, back and forth. Stops. That triggers these various touch receptors. Okay. There's so much more we're not even going into. It makes my head spin to think about it sometimes. But as we do that, you actually trigger another type of neuron that sends an inhibitory stimulus to that nerve ending axon. And it actually stops the pain from being transmitted up in the brain, and you don't perceive it anymore. The same thing happens when, kid falls down. What do you say? Don't baby them. Okay. Don't baby them. If it's just a little fall, pick them up. You just tell them, rub it. And they rub it. And then you're like, don't you feel better? My little boy was like, yeah, I do. The same concept. Okay. By just that little bit of mechanical touch in that region of the pain, you trigger another type of receptor. And that sends an inhibitory stimulus to this one. So when we talked about excitatory postsynaptic potentials and inhibitory postsynaptic potentials, okay, it's triggering an inhibitory postsynaptic potential on the main axon going up, carrying pain into the brain. Right? So there is this thing called a gate pain theory. And it talks about, all of these other various different types of receptors that we're not getting into to actually inhibit pain instead of promote pain. And then there's different receptors, and then there's different neurotransmitters involved, right? We have substance P that gets secreted from a pain receptor and it promotes the perception of pain, right? Well, we have other ones that make you feel good and inhibit pain. And they're going to be, that's the neurotransmitters secreted by these inhibitory neurons that we find. So, I mean, once you know a little bit, you can read into more and understand all of the hows and the whys and of more and more complex stuff. But all this is just the basic building blocks for what in the world is happening inside all of our tiny, tiny, tiny little